sorry. We're going to run through a couple of, a handful of water quality parameters that you'll run into in dealing with water almost anywhere, but particularly in aquaculture. The first one, TDS, stands for total dissolved solids. This is something you would never deal with if you're dealing strictly in marine water, because really TDS and salinity are measuring the same thing, how much dissolved stuff there is in the water, particularly solids. But a TDS meter is really designed for detecting small amounts of dissolved solids. So if you're measuring salinity in salt water, you're essentially measuring TDS, but it's really looking at a different set or a different mixture of dissolved things versus what you're going to find in fresh water. What I mean to say is different proportions. So in salt water, the proportions of the most common dissolved things stays the same wherever you go, regardless of salinity. In fresh water, proportions can vary a lot based on what kind of sediment you're pulling the water out of, or what kind of pipes they're running through. And as it was explained to me by a prominent chemist the other day, TDS really is a term that was invented by the drinking water industry and people that sell Brita filters and things like that. Chemists and marine scientists don't really use it. But it does have relevance when you're talking about your freshwater source, even if you're trying to use pure water to mix synthetic seawater, you kind of want to get an idea of how much dissolved stuff is in there. Do you need to filter it, or is it good enough as is? It doesn't tell you, when you're measuring TDS, it doesn't tell you specifically which ions are there. They could be toxic ones, they could be harmless ones, but it's just giving you a total measurement. So the only way with salinity or with TDS to absolutely directly measure what's there is to evaporate all the water, and what's left behind is your dissolved minerals. So if you take a sample of water and weigh it very carefully, very precisely, and then evaporate all the water away, the little residue that's left, you can weigh that, that's your TDS. And then if you heat up, burn off the other stuff, it'll get a little bit lighter after you heat it up to a certain temperature, and what leaves then is what they call TDVS, total dissolved volatile solids. So volatile just means they're able to go into a gas state. So you can heat them up. It's something we usually don't bother doing. To measure TDS, if it's something that concerns you, you use a TDS meter, which is based on conductivity. It sends an electrical current through the water, and a little receiver picks up how much electricity is able to go across and complete a circuit. A lot of people forget that water really isn't a very good conductor. We all have this idea that water conducts electricity really well, because we've all probably been electrocuted at some point in bare feet, in a puddle, somewhere, where you hear horror stories of an appliance falling into a bathtub and someone getting electrocuted and dying. But water, pure water, is not at all conductive. It's only once there's dissolved solids in there or any kind of ions in there that electricity can flow through it. So that makes a conductivity meter something useful for measuring how many ions are dissolved in water.
So total dissolved volatile solids are organic, or that's what's remaining after the organics are gone?
Those are primarily going to be organics. And how much of it burns off? I mean, mercury is not organic, but if you heat it up enough, it will also go into a gas state. So, but in general, most of the dissolved stuff that's going to burn off are going to be organics.
Okay, thanks.
So we measure it. You can measure it in parts per thousand, grams per liter, PSU, which stands for practical salinity units. Oh, sorry, we're into salinity. That was all I was going to say about about TDS. Salinity, total amount of dissolved ions, and this is something that is, of course, big concern if we're in marine or estuarine waters. You can measure it the same way as you can TDS, of course. And again, the only direct way to measure it, the only direct measurement is to weigh a sample, evaporate off the water, and then weigh what's left. But there are a lot of useful indirect ways of measuring it. We'll go over each of those. And this is why it's a unitless number, because we can't measure it directly. The most common term we use for referring to salinity, or the most common units that we use, are parts per thousand, or PPT, which is the same as grams per liter. You can talk in percents, but then you're not going to be in whole numbers. In percent, so average salinity of seawater is about 34 or 35 parts per thousand. If you convert that to percent, it's going to be 3.4 or 3.5 parts per thousand. So to bring it up to nice whole numbers, we use parts per thousand. So fresh water is going to have a salinity at or around 0. Obviously, if you're measuring TDS in fresh water, you're measuring at much, much lower concentrations. 15 parts per thousand, it would be common in an estuary kind of area, where around the mouth of a river, and fully marine water in the open ocean is up around 35. If you're in an arid, warm climate where there's a lot of evaporation, it can be a little higher. If you're anywhere near a coast where there's any amount of precipitation, on average, it'll be a bit lower. So some of the ways we measure salinity. I think the simplest and most accurate technique is using the refractometer. So again, you're not directly measuring salinity with the refractometer. You're measuring, in a sense, the density, but you're not measuring the density directly either. You're measuring the difference in density between the air and the water sample. And because that, as light, it's really what it's measuring is how much light bends. It's measuring something called the refractive index, or how much light bends when it moves from one medium into another medium. Why does light bend when it moves from one medium into another?
It's a wave?
Well, light moves as a wave, but it's moving through space in a straight line, right? All the light that hits us here is coming from the sun. It's moving through space in all directions in straight lines. So you have a beam of light coming in. All the beams are coming in parallel. And what is the speed of light anyway? Anyone know the speed of light? I forget it in meters now. It's 186,000 miles per second.
Yeah.
But that's the speed of light in a vacuum. The speed of light changes a little bit when it goes from the vacuum of space into our atmosphere. Changes a little bit when it goes from the atmosphere through a glass window or through or into water. And so what happens is the light waves are coming in, and they go from the air to this little plastic lens on here to the water sample that's underneath. You put a drop of water right here, light comes in at an angle, and you have the beams. So you have this thing, your water samples on this lens here. If you have light waves that are all coming in parallel to each other, right? This one's going to hit this sample of water first and slow down first. This one's going to travel a little bit farther at its full speed before it slows down, and this one will, and that, the fact that the timing of these beams all coming in parallel is spaced out. This one hits first, then this one, it causes them to curve slightly, right? Each one, this one, the whole beam ends up bending, and that's called refraction. When light or any wave changes direction because it's moving into some medium of a different density, it's going to bend a little bit because they're not all going to hit at the same time. And so The refractometer measures how much bending takes place when it passes through that little film of water that you place on there. The higher the salinity, on average, the more dense your solution is, because all the stuff that's dissolved in water is more dense than water. And so the more dense, the bigger the density difference between air and water, and the more bending takes place. And it shows up by, it casts a shadow here based on how much bending takes place. Wherever this line is between blue and white is going to show your salinity. So the more it bends, the higher up this line is going to be. The less it bends, the lower it's going to be. If you have fresh water, it's going to be right down at the bottom. You're measuring directly something called the refractive index, which is a measure of, it's a way of measuring the density difference between air. And you use the same tool if you make fruit juice or beer or wine and you're trying to carefully measure how much sugar is in your solution or how much alcohol. That's going to affect the density of your solution of concern too. But when we know we're dealing with amounts of salt, and we don't throw things like sugar or alcohol into the mix, then this gives us a very good gauge of salinity. The one you'd use for fruit juice or for wine or beer would function exactly the same, except the numbers would mean something different on you. This just shows how the refractive index works. You've all probably done this. Looked at a straw or something in a glass of water and see that it looks like it's slightly offset. That's also because of that refraction of light through water. Like any measuring tool, it's important to calibrate it frequently. You put a known sample of purified fresh water in, and then you can adjust this to, that's going to make a little adjustment in the mirror or the lens or something inside that's going to bring this right to zero. So if you put a pure fresh water sample on there, and the lens is clean, there's no salt crystals left behind from last time, you can adjust this right down to zero, and then it'll be calibrated when you put your next sample in. Another tool that we use is called the hydrometer. The hydrometer also is not measuring salinity directly. It's measuring the densities, but it's measuring not even the density. It's measuring the relative density between the water and some floating object. So there's two different styles of hydrometer we use. One is just a glass tube that's closed at both ends and has a calibrated little bunch of lines and numbers on here, and has a very specific amount of weight put in it. And so this glass tube will float in a sample of water, but it'll float higher if the salinity is higher. Remember, if you put more dissolved solids in, this overall density of your solution is higher. And so that means the density relative to this thing is higher. This has a relatively lower density, so it floats up a little bit higher on water. If you put it in fresh water, it'll sink way down. And you may have felt this. If you do a lot of swimming, you'll notice it's easier to swim in salt water, aside from the fear of the sharks and the jellyfish. You float higher on salty water than you do in fresh water. Fresh water, you put in a lot of energy into just keeping your head above water so you can breathe. You sink lower in the water. So the other style has a little, it's hard to make out here, but there's a little arm here and a little disc that, I guess, I don't know if the disc is a weight. It helps. I don't know what the disc.
It's a pin. It's pinned in place.
It's pinned here. That's the hinge where it rotates, and then there's a disc in there that I guess somehow moderates. I don't know. Anyway, this arm will float up a little higher in saltier water or more dense water, and sink down a little lower in water that is less dense. And you'll notice the numbers here are not given in salinity. These numbers are density terms. What they call it specific gravity, what you're measuring with the hydrometer. Specific gravity technically is the relative density, the density of the water sample relative to whatever the thing is that's floating in it. So, anyone know what the density of pure water is?
1.000.
Yeah, it's 1, right? It's 1 watt.
Oh. I don't know.
Doesn't mean anything if you don't know the units.
I know the relative units.
Is it 1? Well, what would you say if someone said fill in the units? What would you write?
I don't know.
Anyone? You know what density is? What's the formula for density?
Mass divided by volume.
Mass over D equals M over V. Density equals mass over volume. So what do you think the units would be for mass that we're going to use in here? Because this is a science class. Grams, right? Grams over what did you say?
CCs.
It's centimeters squares equals cc.
It's definitely not squared because that would just be cube, right? Cubic centimeters. You could say grams over cubic centimeters, or the other term for a cubic centimeter. We use the metric system of volume measurement. A milliliter, right? So, so density is in gram, so it's 1 gram per milliliter, and in fact, that's what our standard is for that. That's where a milliliter or cubic centimeter comes from. So it's based on the density of water, or the mass of water. So we use water for a lot of these metric measurements as the standard, you know. So pure water, 1 or 1.00 gram per cubic centimeter or per milliliter. If you add anything, if you dissolve anything into it, it's going to change the density. So seawater is going to have a density, relative density, specific gravity up around here, right? 1.022 grams per milliliter. Is that about right? Oh, yeah, 1.025. So 35 parts per thousand, 1.025 grams per milliliter. And I always tell my aquarist friends this. Use the right units. So often I'll be talking to someone with a fish tank and they'll tell me they're having a problem or something. I say, well, what salinity are you keeping your tank at? And they'll tell me 22. I say, well, 22 what? Do you mean 22 parts per thousand? Because that's pretty low. Well, I do keep it a little low. 22. What do you use to measure it? A hydrometer. Doesn't say parts per thousand on your hydrometer, probably. What they're doing is saying, well, it's only these last 2 digits here that are changing, so I'm going to just truncate it and ignore all these others. And they're talking, when they say 21 or 22 or 23, what they mean is 1.022 grams per milliliter. So it's a silly thing to do, and it doesn't make any sense, and it's confusing. So it's important, I think, to make sure, especially for communication purposes, that you're using the right units when you're talking about these numbers. And so, yeah, 22. If you say 22, I'm going to assume you mean 22 parts per thousand, and that you're talking about salinity, not density. So these are, again, specific gravity, which is the relative density relative to the thing that's floating in it. 2 types of hydrometer. Conductivity, we mentioned earlier, is you're measuring how well electrons will move through a solution. And the more stuff that's dissolved, the more conductive water is. Again, you have these little electrodes. They get a stream of electrons flowing, and you're measuring how well that electricity is moving across. So if you can do a fun little experiment where you take a battery and attach both ends to a light bulb, but cut one of the wires and send from the battery the wire into a container of water and then another wire out into the light bulb, and the light bulb won't light. But if you sprinkle a little bit of salt in that solution, the light bulb will light up, demonstrating the idea of conductivity and salinity. Turbidity can be important depending on what you're trying to grow. Turbidity is a measure of how murky the water is. It's the opposite of transparency. We use something called a turbidity meter. It's measuring the scattering of light. So turbidity can be caused by anything in the water that's blocking the passage of light through it. Dissolved stuff doesn't impact turbidity at all. It's suspended particles of clay or silt or mud, or plankton, living plankton, phytoplankton, bacteria. It can be caused by any number of things, and it can be used as, in some cases, it can give you a general idea of if you have good. Generally, we think of clear water as being higher in quality, but not all turbidity is equal. If you have turbidity that's caused by something completely inert, clay, which is just very, very, very tiny fragments of rock, it's going to have a different impact than dissolved organics, this black water that's flowing out of all of our rivers right now from all that rainfall. Alkalinity, another term you hear a lot in water quality. So alkalinity is a measure of certain ions. The term gets misused a little bit, and there's a little bit of flexibility in it too. Generally, what we're measuring in alkalinity are these two ions, the carbonate and bicarbonate ion. Although some of these others can be included. Where you want your alkalinity really depends on what you're growing. What your alkalinity is depends on your source water. It depends on the sediments. If you're doing pond culture, the sediments under the pond are going to have a big impact on alkalinity. So the way we measure alkalinity is by using some kind of an indicator solution that will change color at a specific pH, and then adding acid to that solution until the pH reaches that point to make a color change. We call that kind of chemical test a titration. You're adding a little bit at a time until it reaches a specific point and you get a color change. So one way to define alkalinity is the resistance of a solution to change pH, or to lower or to drop in pH when you add an acid. So you can increase alkalinity by adding something like calcium carbonate. That's going to, of course, increase the number of carbonate ions. Or calcium or sodium bicarbonate, baking soda, will increase the number of bicarbonate ions and raise the alkalinity. In general, of course, seawater is going to have a much higher alkalinity than fresh water because it has a lot of dissolved ions that will contribute to it. The higher the alkalinity, again, the more resistant the solution tends to be to changes in pH. So if you take fresh water and salt water and add a little bit of acid to each one, you'll see that the pH went down in the freshwater sample and maybe didn't change at all in the saltwater sample. And that brings up another term we call buffering. We'll talk more about that when we get to the pH chapter in a minute. You have a lot of different causes of drops in alkalinity, but again, where you want your alkalinity depends on what you're growing. If you're growing catfish, well, for one thing, they're going to be very forgiving of a wide range of conditions, including alkalinity, but they're going to tolerate very low alkalinity. If you're growing African cichlids, you're going to need your alkalinity much higher because they grow in alkaline lakes. In general, you're going to have alkalinities going to drop with the activity of certain bacteria. If you're growing corals, they're going to naturally reduce alkalinity because they're going to be removing carbonate ions, calcium and carbonate ions from the water. You need to constantly adjust. If you have a tank with a lot of corals in it, you'll need to constantly be adjusting your alkalinity. In a good, well-filtered system where it's fish only, you're probably not going to need to. You're probably not even going to bother testing alkalinity very often.
I have two questions. The first would be, do soft corals pull alkalinity as well, just at a lower rate, or not as much?
Most of them, I would say, do, but
Okay.
not nearly as much. Hard corals are going to have a much bigger impact on alkalinity. Hard corals have skeletons made of calcium carbonate. Most soft corals, some soft corals like Dendronepthia has little calcium carbonate sort of spines in it, but it doesn't have a big solid skeleton like the way an acropora would.
Yeah. Okay. And then my second question was that I'd always been told that alkalinity lowers over time in a confined tank. Is that specifically because corals are removing it, or does it, regardless of the presence of corals, still lower over time?
Well, I think over time it's going to lower in almost any tank,
Okay.
whether there's corals or not. Bacterial growth.
The bacteria that consume the ammonia are using the carbonate ions as a carbon source to complete that nitrification reaction. So
okay.
Alkalinity is consumed during nitrification.
But not the bicarbonate component of it.
Both, I mean,
Okay.
carbonate and bicarbonate. It's consumed and alkalinity will drop, and if once you get below the threshold, biofiltration stops.
Okay.
So having alkalinity below, 50 or 40 or 50 milligrams per liter, you basically have no biofiltration capacity at all because there's not enough carbon source for the bacteria to do their job.
Okay.
And as you'll see in a minute, if you remove carbonate ions, it's going to reduce the number of bicarbonate ions.
Okay.
Always. And you'll see why in a
Thank
second.
you.
Total hardness, again, this is something that you're mostly going to be concerned with in freshwater systems, but hardness specifically is measuring concentration of metal ions. So if you have hard water at home, then you're going to have problems in your pipes. You're going to have calcification. You're going to have this scaly stuff developing on your plumbing and in your sinks and things. And that can be a problem in an aquarium or an aquaculture system. And even if it's hard, if it's at a hardness where the fish can deal with it, you might say, all right, so the fish can deal with it. But why is it going to build up in your tank over time if you're using kind of hard water? Even if it's, as it comes in, it's good enough. But over time, water is going to be evaporating from your tank. You're going to do water changes, but you're going to be starting with what's in there is going to have a higher mineral content. And that constant evaporation, even if you're doing, daily or weekly water changes, it's going to build up. So if you have very hard water, you're probably going to want to take action to remove it. Primarily, calcium and magnesium are involved when we are talking about water's hardness. Of course, if it's too soft, that can cause other issues. Certain organisms, whether you're talking about, freshwater shellfish or marine shellfish, they need some of those minerals in there to make their exoskeletons, or to get even fish. They unlike us, fish don't get all of their calcium from eating. They get some of it from the water, and they get some of it from things that they eat in the water that absorb it out. So if you have it too low in these minerals, it can cause problems for certain organisms. This is a table. All these slides, keep in mind, are posted online, so don't worry about getting all this stuff down when you see a slide like this. It shows some different units that are used for water hardness. Degree of hardness, so we're measuring it in what is millimoles per liter or in parts per million. I don't ever deal with hardness, so these are here for reference if it's something that you are interested in. But what can you do to soften your water? Well, you get a water softener. And there's a few different ways to do it. One of the most common ways to reduce hardness is to use an RO filter, and you can use that to remove any kind of dissolved solids from your water source. Basically, you know what osmosis is. What's osmosis? Go back to your 4th grade science lesson. What is osmosis?
Really? That's great.
The transportation of water through a membrane.
It's the movement of water across a membrane that doesn't let other stuff across. So water all on its own will cross a membrane like a cell membrane or the membrane filter in an RO unit. And so if you have water water with a high mineral content on one side of a membrane, so a container of water and a membrane separating it, and if the water on this side of the membrane has a lot of dissolved minerals in it, and the water on this side has none, the water is going to cross the membrane this way, all on its own, because these dissolved minerals can't cross the membrane. Water can, and water, like anything in solution, has this need to move from an area of higher to lower concentration. The water concentration here is higher than here. What do you call that, moving from an area of higher to lower concentration?
Dilution.
If I had another container of water with no membrane, and I put a few salt crystals in here, they would dissolve, and these dissolved salt ions would continue to spread in all directions until they were perfectly evenly distributed. What's that process called? It wouldn't happen if they weren't actually dissolved, if they were just suspended particles. But since they're in solution, they're going to move from an area of higher to lower concentration. And what do we call that process? Finn, what's the answer? It's diffusion. Movement of anything in solution from an area to higher, from higher to lower concentration. So water, this is diffusion. Osmosis is a subset of diffusion. It's a type of diffusion. But it's water crossing a membrane, going from an area of higher to lower concentration to the point where it can even overcome gravity a little bit, and the water level on this side will rise. That's osmosis. Reverse osmosis means that we apply some kind of pressure on one side of the membrane and push the water back across against its concentration gradient to purify it. So we're forcing water across one of these membranes against the way that it wants to go. That's reverse osmosis. That's the way. And RO stands for reverse osmosis. That's the way they work. Also, you can use resins, ion exchange resins, that will pull out specific ions that they're tailored to. Often you get, in one of these filter kits, you'll get an RO membrane and also an ion exchange resin to pull out anything that is missed in the RO portion. If you're applying too much pressure, certain minerals can make it across the membrane.
That's the DI bit, correct?
Yeah, they call it RODI. Reverse osmosis deionization. Puts the two together will get you a really pure water sample.
You don't want to put that in a fishbowl, correct?
What's that?
After you send it through an RO and all that, you don't want that.
You don't want to keep most fish in water that's been through an RO DI filter unless if you're keeping